This is CBS Eye on the World. I'm John Batchelor. Hotel Mars, Episode N. David Livingston, Dr. Space himself, is here with me, and we're headed to Mars thanks to Michael Hecht. Michael is the Associate Director at Haystack Observatory, MIT, but most importantly, he's the Principal Investigator on a toaster, so-called metaphor by the Washington Post, a toaster on board Perseverance, the rover on the surface of Mars, Jezero Crater. And this toaster, this MOXIE, which Michael will demonstrate for us, is a road to the future of Martian colonization. This is not Hollywood anymore. This is an experiment that works. Michael, congratulations. Good evening. Introduce us to MOXIE, which of course for an acronym, but in any event, I love the name MOXIE. What is it meant to do, Michael? Thank you.
Very glad to be here, and thank you for letting me talk about one of my favorite subjects. MOXIE is going to solve a big problem for us when we go to Mars someday, when maybe my grandchildren or yours go to Mars. And, you know, when Lewis and Clark set off across the United States, they brought all the things they needed, from ammunition to food, but they did not have to worry about oxygen. When we go to Mars, there's a beautiful planet waiting for us to explore, and it's got lots that we need, but no oxygen. And sometimes we don't think about the fact that we not only need that oxygen to breathe, which we then use to help turn our fuel, our food, into energy, but we need it for any other fuel we turn into energy, whether it's our car or our campfire, or most importantly, the rockets that take us to and from the planet Mars. So we could bring tons and tons and tons of oxygen with us every time we go to Mars, or we can make it there. And MOXIE is showing that indeed we can make it there. And I'd like to think this will bring the day that we actually set foot as a species on Mars, 10 years or more closer, by being able to make the oxygen we need out of thin Martian air. The Martian air is indeed very thin. It's less than 1% as thick as the air here on Earth, but it is almost entirely carbon dioxide, which contains within it oxygen. So the trick is to make like a tree and to extract that oxygen from the carbon dioxide. Well, we can't send a grove of trees to Mars, but we can send MOXIE.
Mars Oxygen In Situ Resource Utilization Experiment, hence MOXIE. David, you have a question for Michael.
Is CO2 the only thing it's converting, or what else is in the Martian atmosphere that adds to the conversion to O2?
CO2 is about 96% of the atmosphere on Mars. The rest is argon and nitrogen, which by themselves would be very useful. Right now, they just pass on through MOXIE out the other side, but in a future version, we might collect them to use for different purposes. The only thing making the oxygen today and in the foreseeable future is carbon dioxide. Someday, we will also explore Mars and collect water, collect ice, and that's another ingredient we can use to make not only oxygen, but fuel, and who knows, maybe someday vodka. I don't know.
So this is chemistry, fundamental chemistry. You've got a machine, MOXIE, a robot, that converts CO2 into oxygen. How does it do that, Michael? Can you give us a formula, or is it like a magical Jules Verne episode where you push the raw material in one side and out the other side comes a magic weapon?
Let me try a few different ways. A formula, sure. Two CO2 molecules. 2 CO2 goes to 2 CO, carbon monoxide, and 1 O2, 1 oxygen molecule. So what does that all mean? That means we're taking 1 carbon dioxide molecule, which has 1 carbon and 2 oxygen atoms, and we're carefully pulling off one of those oxygen atoms, leaving the other one alone, so that what's left behind is carbon monoxide gas, which will harmlessly go away. If we pulled them both off, we'd have carbon, and quite frankly, that would make a mess and stop the instrument from working. So the art is to pull one oxygen atom off. That's the chemical formula. How do we do that? It's surprisingly like a fuel cell. And I think most people have some idea how fuel cells work. They're kind of like an engine, but nothing burns. Instead of making heat, you make electricity directly from reacting to chemicals. MOXIE is a sort of fuel cell, but instead of reacting to chemicals to make electricity, it runs the other way. So it uses electricity to pull apart those molecules and make the fuel.
So the power, Frankenstein needed power too, lightning. So the power is like Frankenstein. You introduce electricity and it separates CO2 into carbon monoxide, and the oxygen is then collected by MOXIE?
Well, this little version of MOXIE here is to show that we can do it on Mars. So we do very little more with the oxygen than simply measure it, make sure it's pure, and then catch and release, send it on its way, send it back out to the Mars atmosphere. But in the future, it'll get put in a tank of liquid oxygen like you see strapped to the bottom of a rocket.
David, you have a question.
This is similar to photosynthesis. So which process is more efficient and how do they differ? So if you had a plant versus MOXIE, what would we expect the difference to be?
Oh, that's a really interesting question. Plants, of course, do more than convert CO2 to oxygen. They're not that altruistic. They're out for themselves. And so what they do is they take carbon dioxide and they take water and they make carbohydrates, which is their food, and they release oxygen. MOXIE just does half of that process, and it does it with a catalytical chemical method through a membrane. But someday, when we have water on Mars, then we'll be doing something much more like a tree, where we'll be starting with water and oxygen, just like the trees, and we'll put them together and we'll make oxygen and fuel, probably something like methane. So next generation, it'll be even more like a tree.
I read there's a history with MOXIE. You started in the spring of 2021 in Jezero Crater, where Perseverance is, and you made a little less than 6 grams. But now I read you've made 10 grams. So MOXIE is getting better at extracting oxygen. You're learning to be more efficient. What explains what is apparently your cup runneth over?
There are two things that are changing. One is simply that we're getting more confident. When I mentioned when we run MOXIE, you have to be very careful not to push it too hard. If you push it too hard, you start making carbon. Which the ironic thing, by the way, you call that process coking, and you call that carbon coke. And of course, MOXIE is a soft drink. Coke is a soft drink. They were once competitors. They're still competitors. Coke will destroy MOXIE. So as we learn more about the instrument, we've gotten more confident pushing it harder and harder toward that limit without actually crossing it. Now, the other thing that's changed, though, is Mars. And Mars has seasons and has climate and has weather. And as the year has gone by, the atmosphere has gotten thicker and thicker. And then it's starting just right now to start getting thinner again. So we took advantage of that thicker atmosphere to make more oxygen.
David, you have a question.
If you are making this oxygen, theoretically, what type of scaling up would it have to go through to support a crewed mission to Mars of, say, 6 people? I mean, I know you're not near that now, but what are you dreaming about in the future?
Well, it's not as far away as you think to be able to support a crew of 6 astronauts. First of all, what does that mean? The astronauts themselves, in terms of breathing, they might need in the course of their, we expect a human mission to be about 1.5 years on the surface. That has to do with how the planets line up. And over the course of that 1.5 years, 6 astronauts might use, let's say, 3 tons of oxygen, which is an awful lot. But the rocket that takes them off the surface to get them on their way home is going to use closer to 30 tons, 10 times as much. Rockets breathe a lot more than people do. And so we're going to need 30 plus tons for those 6 people. That means we need to make 2 to 3 kilograms an hour of oxygen. to fill up that tank in time for the crew to arrive. Right now, we're making 6 or 10 grams. So that's scaling up by 200 or more, but it's not as hard as it sounds. The main reason we make so little oxygen is because the rover has a tiny little power plant. It can deliver us 100 watts of power like a light bulb. The human mission, for the people to do their thing and survive, is going to need 20 or 30 kilowatts of power. If you gave us that today, we can make you your 2 or 3 kilograms of oxygen an hour today. It's just a matter of having enough power.
We're speaking to Michael Hecht. He is the Associate Director at Haystack Observatory, MIT. He is, most importantly, the Principal Investigator on the NASA experiment on board Perseverance called MOXIE. Hotel Mars is a construction in my imagination. I do not believe I'll reach the planet Mars. I'm not certain I'll see man and woman reach the planet Mars, but oxygen is the hook that we have. And Michael, as the principal investigator on the experiment MOXIE that is on board Perseverance right now in Jezero Crater, has given us to understand that making oxygen is something that's imaginable. The chemistry is very straightforward. You need power to do it, and you need scale to provide for human beings. However, Michael, I come to you on this puzzle. You have an unlimited budget now, and the question of producing oxygen for a 4 or 6 person mission is a challenge. That's frontier thinking. You know, first you have to get there and see how you can survive, not on the surface, probably under the surface. What I'm imagining is a Mars colony that uses lava tubes because they're hollowed out underneath. It would protect you from the dangers of the surface of Mars because the very thin atmosphere doesn't protect the way our atmosphere does. Are you at MIT, are you at JPL or NASA already working on that scale? And is that scale imaginable to fill a lava tube or a constrained space with oxygen on a continual basis so that we're manufacturing Earth-like conditions? Admittedly, the gravity is not anywhere close to what we have here on Earth. It'll change us. But maintaining an atmosphere that not only can make humans breathe, but also sustain plant life and agrarian life and growing things. Is that already on the drawing board, Michael?
It is absolutely on the drawing board, and let me give you an idea of how that will work. If we have, let's suppose we have 100 people in that lava tube. That's a really good start toward a sustained presence on Mars. That's a research station at least. Those 100 people, in terms of breathing and in terms of, you know, the things that they'll use cooking and whatnot, will probably use 20 or 30 grams an hour of oxygen. So let's say 2 to 3 kilograms an hour to keep that whole lava tube community, you know, going and thriving. That's about the same amount that we're planning to make just to fill up a tank of oxygen for a rocket. So the lava tube is the easy part. We could do that if you gave me the budget that you offered. We could start that tomorrow.
Just write your own check.
Write our own check. We could start doing that tomorrow. I've always, thought that doing a full-scale MOXIE is no harder than doing the one that we've done. It just is bigger and needs more power that we don't have on Mars. So yes, we're ready to build that system, and you'd have one system maybe in the lava tube, and you'd have a much bigger one outside to just as a rocket fuel factory. And then we'd invest in the ability in robotic trucks and cars to drive up to the north where there's permafrost and ice, and to dig up ice and bring it back. So now we can use water and oxygen to do chemistry and make fuel and all sorts of things that we need. And I even love the idea of having, you mentioned MOXIE in a backpack, of having something like, I think of the mini split units we put on our walls to do heating and cooling, and adding MOXIE to that. So we'll get warm air, cold air, and oxygen and carbon dioxide scrubbing all in one climate unit that we can put in our cars and our rovers and in our homes and in our gazebos.
David?
Does any of this lead toward and support terraforming, or is that a totally different topic and situation?
Terraforming on Mars or on Earth, for that matter, is a totally different situation. I constantly get asked about the Earth situation. Can't you use this to do something about climate change? And the answer is, not really. This still takes a lot of energy. And the first thing we have to use learn for climate change is how to produce lots of energy without carbon dioxide. Terraforming Mars is the same thing. The scale, it's just too big to imagine the energy source. So when people talk about terraforming on Mars, they're talking about things like, darkening the polar cap so they'll absorb more light. Things that can leverage the existing solar input and the existing weather cycles on Mars to change the climate, just as unfortunately we're changing it on Earth.
You mentioned the extracting from the permafrost. A water source is necessary to sustain life. Can a machine get oxygen out of the water as well, not just the atmosphere, but the melted ice that we know is on the surface almost everywhere on Mars?
Well, that's an experiment that many of us do, and maybe even junior high school, where you put a couple of wires in water and you see bubbles of hydrogen and bubbles of oxygen coming off. So yes, once we have water, you could use that as an oxygen source. People usually talk, though, about using both water and carbon dioxide, again, like a tree, to at the same time make fuel and make oxygen together. And that might look a lot like MOXIE, or it might be a different technology. But there is a version of MOXIE currently running. Our partners in Salt Lake City, who developed this little electrolysis unit, what we call the SOx here, the solid oxide electrolysis, who are using both water and carbon dioxide in a process they call co-electrolysis to make two products, one of which is oxygen.
Michael, this century, you imagine we can do this century? Yes?
Now you're asking me political questions. If we had the will,
and the budget,
we certainly could. When I first got involved in human exploration in technology for sending people to Mars, it was back in 1996, I think. And Dan Golden was the head of NASA at the time, and he said 15 years we'll be ready to send people to Mars. It's still 15 years, but I do think the commitment is there now, and that this is going to happen.
Michael Hecht, Associate Director, Haystack Observatory, MIT, Principal Investigator, MOXIE on board, Perseverance, David Livingston, Dr. Space of the Space Show, Hotel Mars episode, and I'm John Batchelor.